Well, here we are again. And one of my responsibilities, I think, as a teacher is to try to help you find relevance in the things that you're asked to learn. If you go back to the learning objectives for Unit 1, you'll find that we're reviewing the anatomy of an atom. Well, why? Who cares? There are a couple reasons why you should care and why it is relevant to your health and well-being and anatomy and physiology. So let me show you what those are. First, let's start with an atom. And we're going to look at a compound, sodium chloride, simple table salt. It is a crystal in the dry form, and it is a situation where the sodium and the chloride are charged when they dissociate in solution. In other words, you put them in water and dissolve them in water and they dissociate. Sodium is positive and chlorine is negative. Why is that? It's because chlorine has stolen an electron from sodium. So if I use my iPad here for a moment, now that I'm done playing quiz up, that you'll notice is on one of the definitions. There, I get it right. Okay, there it is. Sodium and chloride. The nucleus of the atom, of each of these atoms, is made up of protons and neutrons, and there's an electron cloud spinning around the outside. The electrons are so small compared to the protons and neutrons that we sort of ignore them in terms of atomic mass, but they do have mass. But they are 1/2000th the size or the mass of a proton or a neutron. So what happens with an ionic bond is, in this case, chlorine, oops, I get my face too much in there, chlorine steals an electron from sodium so that when these dissociate in water, when they dissolve in water, as they are in your body, chlorine is negative and sodium is positive, and these atoms in particular are very important in the physiology of your body. But that's not really the subject today, but we will talk about that later. Several salts, which are not organic compounds, they're inorganic, are parts of your body. And they're very important for physiology, for muscle contraction, and for nervous transmission. And without proper levels of those, homeostatic levels, you will die. In fact, in the one case, calcium is so extremely important that, go to this again, calcium is so extremely important that if blood levels fall very far, you will have a heart attack and die, because your heart has to have calcium in order to keep beating. And all of your muscles need calcium in order to contract, and all of your nerves need calcium in order to, and they also need sodium and potassium ions in order to function properly. But there are two medical reasons besides that that are pretty important for studying atoms, and one relates to free radicals. Now, you've probably heard that some foods that you eat are antioxidants. They are. And free radicals are charged organic compounds. Any kind of an organic molecule in your body could become charged by accident. Most of them are not supposed to be charged. They're supposed to be neutral. But they can get charged by toxic things that you put in your body, like alcohol and other poisons that we breathe in that are in our air pollution, by cigarette smoke, and so forth. When those compounds, when individual molecules become charged, it's like a bad boy. They go out looking for trouble because charged particles are reactive. And because they're reactive, they can cause damage to other parts of cells, and they can actually cause cancer. So we eat certain foods because they are known to be antioxidants, which means they repair the free radicals. They move electrons back where they should be and allow those molecules to be, again, neutral. But there's another reason that we should understand something about atoms. So let me go back to this figure a minute. Okay, so we have these electrons spinning around, and we have protons and neutrons in the center of every atom. And then we have certain atoms that we call isotopes. And an isotope is an element, an atom of an element that has a different number of neutrons. And sometimes those atoms are radioactive because they disintegrate. They can't hold together. There's an imbalance. So we get radiation. When we get radiation, we can have electrons flying off. Those are called beta particles. We can have protons falling off. Those are called alpha particles. Or we can have a phenomenon whereby gamma rays are produced. Gamma rays are very powerful rays, and to protect yourself from them in a very strong, if there's a very strong radioactive source, you need lead shields and so forth. You need to be way away from those sources. But there's natural background radiation in our atmosphere, and I'm going to show you some. Here you go. So what this is, there's a video, and I'll put the link for you to look at this all the way through yourself.
Cloud chamber. You
heard her say cloud chamber. This is a diffusion cloud chamber in the Museum Technique in Berlin. They're pretty simple to build. They basically are an aquarium within which we create a very strong supersaturated atmosphere made of alcohol vapor. And when a radioactive particle flies through this, it makes a track like an airplane in the sky because it causes condensation of molecules in that cloud. So each of these tracks in this particular part of this video that you see, these white tracks, is a gamma ray. Later in the video, she's going to demonstrate some other.
The particle radiation in it. The thick and short trails are from alpha radiation, and the long and thin ones are from beta radiation. It works by creating a large temperature gradient between the bottom and the...
Okay, so what we're looking at is gamma rays zipping through. Then when she puts, I don't know if you saw the little fat one.
Top by effectively cooling the bottom and heat. Natural background radiation.
There's a fat one there.
That is all around you at any given time. So today there was actually a really cool demonstration of the hole you can see on the top right there. Because you can see all those little alpha particles.
Okay, she's putting an alpha emitter in here. So we get a lot of radioactive decay of this particular compound. Those alpha rays don't travel very far. And so whenever we encounter those in the environment, they don't make it through our skin and they don't cause us much trouble. The same is true of beta rays, which are electrons that disintegrate from atoms. And they're natural. Gamma radiation is natural. There's a certain amount of this radiation all around us, the gamma radiation, that causes cancer. About 15% of all cancers are caused by natural background radiation. But there's another source of radiation that is in our environment and that we are concerned about, and it produces alpha rays, and that is radon gas, which can accumulate, especially in certain areas of the country like Wisconsin, in our basements, in the atmosphere in our basements, because it is emitted from the soil. And we have to clear that air out to reduce the concentration of those rays. Now, if it doesn't go through your skin, why is it important? Because that radiation is breathed in, and then it becomes in contact with the soft tissues of your lungs and can cause significant increases in lung cancer. In fact, if you live in a basement apartment that's high in radon gas and you're a smoker, you have a 200 times greater chance of developing cancer than somebody who does not smoke and lives upstairs where the air is less concentrated with radon gas. So that's particularly important. So I'm not going to play all of this, but I will refer to it. And you can find it, if you don't remember the link, just by looking at just diffusion cloud chamber, and you'll find this video from Berlin. And it's the best one on the internet that shows you this thing.
Being ejected from that source.
Look at that go.
There will be something even cooler later on in the demonstration.
Yeah. So that'll tease you. You can look at this whole demonstration. It's only 3.5 minutes long, something like that. Okay. So the two reasons you should learn about atoms and understand their structure is because radioactive isotopes are in our environment. They are not just in atomic bombs. Some of the radioactive isotopes in our environment actually came from atomic bombs, and they get in our food. Strontium-90 and cesium-137 are radioactive isotopes that last about, half-life is about 30 years. So most of it's now gone from our environment, but at one point in time it polluted our environment all over the northern hemisphere from atmospheric testing of atomic bombs and got into milk. So we were feeding it to children, we were eating it ourselves, it was all over our pastures, and it was a serious concern. And in fact, the health concerns that resulted from atomic bomb testing in the atmosphere were the reason, at least one of the major reasons, that John Kennedy and Premier Khrushchev from Russia decided, or from the Soviet Union, decided to sign a non-proliferation treaty and to ban atmospheric nuclear testing. Once they discovered they were poisoning children. Yeah, pretty important study that was done. So, radioactive isotopes and free radicals in your body that can be created by radioactive isotopes or other toxic substances are serious health concerns and can result in cancer because they can result in deformation of nucleic acids, replacement of genes with broken genes that can result in problems in your body. Okay, I hope that was helpful, and if you found it interesting, watch the video on the diffusion cloud chamber and realize that these things are all around us all the time, and gamma rays are zipping through your body all day long and all night long, and you can't stop it. But it's just a part of nature.